Before we proceed to the first classification of differential equation, let's try to review the ordinary derivative and the partial derivative and how are they different from one another. So let's have the examples and of course their definition. Let's start with ordinary derivative, okay? So that later on as we move into the types of differential equation, we'll be able to understand how they are also different from one another. The ordinary derivative is actually the rate of change, okay, of a certain function. Let's say the rate of change of a certain function, okay, a certain function with one independent variable, okay. So we also have a video on this playlist talking about the independent and dependent variables. So you might want to review on that so that you can also grasp the idea here. So say for example, if we are given with a certain function y of x, so meaning it's a function y in terms of x, let's say x cubed plus 2x, the ordinary derivative, or specifically the ordinary first order derivative of this, dy over dx, or the first order derivative of y with respect to x, is considering that we are going to take the derivative of y with one type of independent variable here. We know that this notation at the bottom talks about your independent variable, and this is actually for your dependent variable. So if we're going to operate this and get its first order derivative, specifically the ordinary derivative, it's actually equal to, okay, so we have here the first order derivative of y with respect to x is we're going to take the derivative of the functions x on this given equation or given side of the equation. Of course, we know that the derivative of x cubed is actually 3x, and for 2x is 2, considering that x is our variable here. So this is how we actually illustrate ordinary derivative. Again, it has only one independent variable. You can even solve for the second order derivative of that. And this is still considered as an ordinary derivative because you are just having one or singular independent variable here. So you're going to treat your y again as your function or your dependent variable and get its second order derivative. Now, as for the partial derivative, a partial derivative, this talks about still the rate of change of a function with two or more independent variables. So this time we may have two or more independent variables, but we have here a continuation for this with respect to one variable at a time. Okay, that's why it's called a partial derivative, because you have two or more independent variables. So sorry, this would be variable, two or more independent variables, but you are just going to take a certain derivative of one of those of one function with respect to one independent variable at a time. We usually use this notation, okay? That's actually a shorter way or a classy way to write your Greek letter delta to illustrate a certain partial derivative. So one of which is, say for example, you have a partial derivative of d with respect to, partial with respect to x. If you have two independent variables, let's say x and y, so you have the partial derivative of f with respect to y. So this could be done in just one example or one function, considering that our independent variables here, look at this one here. For the first one, our independent variable is x, but at the second one, it's actually your y on the same dependent variable. So this would be an example to that, and let me provide you with one example. Let's say for example, you have here a function with two variables. Let's say it expresses 2x squared y plus 3y. Okay? So let's say that we are taking the partial derivative of f with respect to x. So we'll have the notation, the partial derivative of f with respect to x. What does this imply to the variable y? If we're going to take partial derivative with respect to one variable, specifically x here, at a time, we are going to treat, this means treat y as a constant. In short, this would be a constant, that would be a constant as well, and considering that to be a numerical coefficient, when we try to take its derivative together with all the rules of differentiation, we need to actually treat that as a constant in itself. So if we're going to take here the partial derivative of x with respect, f with respect to x, we are taking the partial derivative of your function x squared y plus 3y with respect to x, treating y as a constant. So what will happen here is you can have something like this. It will actually, of course, if you would like to take the derivative of the first with respect to x, treating this as a constant, take note, if that is a constant, it's similar to this form. Okay, we have 2 as a constant. So we're just going to take the constant in itself and then take the derivative of this. So you have your 2x. That's why this is actually 4x. Okay, if you're going to take the derivative of this. So similarly, y would be the constant. So y would retain in itself and take the derivative of x squared because we're taking the derivative with respect to x. So you will have here a certain value of 2x and then your y. Just like here, 2x and 2. Now, for the second given here, let's say this is actually y with y as a constant. That would mean the entire term here is a constant and the derivative of the constant is actually 0. So the partial derivative of f with respect to x is actually 2xy. This is the partial derivative, okay, of the given function with respect to x. And this may not be the same as we are going to treat or solve for the partial derivative of f with respect to y, because this time we are going to treat x as a constant. In short, our function earlier is actually x squared y plus 3y here. So if we're going to take about the partial derivative of f with respect to y, you will be taking the partial derivative of the entire function, treating x, this one here, treating x as a constant. So regardless of the exponent, that is an entirely constant. And just like any form, just like say for example, if that's a constant, 2y, if we're going to take the derivative of that, considering that 2 is a constant, we will get actually 2 by deriving or by rules of differentiation for y to the power of 1. So for this, if we're going to solve for the partial derivative of our function x squared y plus 3y with respect to y, considering that x is constant, what happens here is actually you will just be having you'll be having not y because 2 is retained, right? So this would be using the rules of differentiation. So your constant will be retained, x squared, and then you have here plus the derivative of this, considering that we are taking the with respect to y, the derivative with respect to y is 3. This is the partial derivative of f with respect to y. As you can see, these two are not the same because we are having two different independent variables here. So the partial derivative can be of different forms depending on which variable or independent variable you're considering to be connected to your partial derivative. But the ordinary derivative earlier is treating, since we only have one independent variable, so we don't have any other problem to consider, so we can actually take its derivative automatically. Okay, so this is how the two are different, because later on we will be talking about types of differential equation. First is ordinary differential equation. It would include ordinary derivatives. And for the partial differential equation, we're to be talking about differential equation with partial derivatives. We will have that on a separate video. Thank you very much for watching.